centimetre off, and I'm measuring a length of 10 centimetres and I'm 1 centimetre off. Obviously, that centimetre makes a much bigger difference if you're doing 10 centimetres versus the kilometre. Does that make sense?
Yeah.
So when
Miss,
we're
what page is this?
This is page 175. Actually,
Right.
have I shared my screen yet? Let me get it. Yeah. Sorry, I'm just getting it set up. Is that all right? Can you see that now?
Yeah, that's grand, thanks.
So when you're doing percentage error, it's much more kind of relevant to get the percentage error rather than the actual error. So what you do is you get the actual error. So you do, the difference between what you know is the true value and what you've measured. And then it's as a percentage of the true value, because you're not interested. There's no point in getting the error as a percentage of the wrong value, okay? So it's the actual error over the true value, and then you convert it to a percentage. So remember, a percent is just a different way of writing a decimal or a fraction. So you make your fraction first. So you get your actual error by subtraction. Put that over the true value, and that gives you your percentage error, okay? So the example they give there, John estimated the volume of a liquid to be 100. The actual error, or the actual measurement, was 125. So the actual error is the true value minus the measured or the estimated value. Okay, so that's 125 minus 100. So the actual error is 25 mil. Now, 25 mil, if you were measuring like 10,000 litres, it's not a big deal, but he's only measuring 100 mil. So that's quite, when you change that to a percentage, it's 25 over the actual value, and the actual value is 125. So you put it over the true value, because there's no point in getting a percentage of an error. You want the percentage of the true value, multiply that by 100, and you get 20%. So his percent error is 20%. Okay? That's straightforward enough. You would have done that at junior cycle, I think, anyway. Yeah?
Yeah.
Okay, now tolerance is a slightly different thing. So anytime we go to measure something, whether it's with a ruler or with the weighing scales, or a graduated cylinder, if you're measuring volume of liquid, we have a scale. And it only gives us correct to a certain number of decimals. Okay, and that's where we get into tolerance. Okay, so with tolerance, basically when you're reading it, well, there's two kind of things we want to look at here: tolerance and degrees of accuracy. Okay, so the tolerance is kind of allowing that the scale might be a little bit off and you might be a little bit off. So you look at the smallest unit you're measuring. So if you were measuring, no, sorry, I'm just looking to see. Right, so if I was measuring this on the inches here, okay, and that's split into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so my tolerance, any measurement I make would be within 1/16 either side of that, okay, because that's the smallest measurement there. Now, on the other hand, if I go to my centimeters here, any measurement I make, I can't get more accurate than 1 millimeter. That's the most precise accuracy. Like I could say, okay, it's in between those two, so I could say it's 0.25 millimeters, but I'm really only guessing. So I have to take kind of to the smallest actual measurement is my tolerance. So if we just kind of read through that, if a measurement is taken against a scale, so for instance, a ruler or a balance measuring mass or a clock measuring time, the accuracy is limited by the size of the smallest unit, okay? So on a ruler, it's normally millimeters. On a balance, it's normally grams or ounces. In a clock, it's obviously seconds. And so your tolerance is you take your smallest unit, so this, in this case, would be millimeters, okay? So your tolerance is you're going to say I'm accurate to either plus or minus a half of that, so 1/2 of a millimeter, okay? Because you can't go accurately less than a millimeter. So wherever you get, you're within a half of one either side of that. Does that make sense?
Yeah.
Yeah.
So it's always a half of the smallest unit you can make, and it's plus or minus that. So you could say, okay, I'm measuring that to 11.2 centimeters plus, but it could be 11.15 or it could be 11.25. Okay, so my tolerance is plus or minus a half. Does that make sense?
Yeah.
Yeah.
So like if I was measuring here, I'd say, okay, that's 12.6 millimeters plus or minus a half a millimeter. So it could be 12.55 or it could be 12.65. It's somewhere in between those two values. Okay. So that's what tolerance is. And the thing to be careful of is when you're doing area or volume, each dimension has a similar tolerance. So if you're doing an area, so for instance, say you read 2.5 centimeters for length, okay, and 3.2 centimeters for width, all right, and you're doing millimeters, okay. So your actual reading there would be 2.45 up to 2.55 could be the range, and the range here could be 3.15 up to 3.25. Does that make sense?
Yeah.
Yeah.
Okay. So if they ask you for the variation in area, you're not saying it's plus or minus a half a centimeter. You're saying, okay, well, the area, the smallest possible area would be the smallest length by the smallest width, and the largest would be the largest length by the largest width. So when you multiply those, you end up with a completely different tolerance than just the length or the width. Okay, so we'll look at some examples of that. So just be careful when you have 2D or 3D, your tolerance comes into play for every single dimension. Okay, so, and usually they're asking for the difference between the minimum area or the minimum volume and the maximum. So get all your minimum dimensions, multiply them, all your maximum, multiply those, and then look at the difference, okay? And then the last thing we want to look at when we're measuring is how accurate it is. So degrees of accuracy. So obviously when you're rounding off something or you're reading a length, so if it's given to a degree of accuracy, correct 1 decimal places, that's an error as well because you're rounding. Okay, so degrees of accuracy is due to rounding, tolerance is due to the actual scale. So if you're given a length as 10.3, correct 1 place of decimals, then you know that, okay, it could have been rounded up from anything from 10.25 up to, 10.99, or it could have been rounded down from 10.3, whatever, up to 3.4999, because it was if it was 10.35, it would have been rounded up to 10.4. Does that make sense? So the actual length is anywhere in between those. Is that okay?
Yeah.
Yeah.
So you're just adding in 1 extra position in your decimals. So you're going to 2 decimals and you're going, okay, it has to be, I'm starting at 0.5 and I'm finishing at 0.4999, okay? And so there's a couple of examples in showing this, and the focus on these is kind of looking at the errors rather than looking at the actual calculations. So example 1 is the cone and the frustum of a cone. Find the volume, correct 1, place a decimal. Okay, then you're just rounding. Okay, so we know, and I noticed some people, for the frustum of a cone, there is a formula in the tables, but they prefer you to do it using similar triangles. So you can use this formula here, where you've got the base of the large part and base of the smaller part. Okay, and the formulas for surface area and volume there. But as I say, they tend to prefer you to use similar triangles. So if you imagine a cone would keep going up to here. So if this is 6 and this is 4, Then if you draw a triangle kind of representing that, that's 6 and 4. And that's 8. Sorry, 8. Sorry. That's 8. What you want to do is get the entire cone minus the bit on top. Okay, and to do that, we need this height here. Okay, so 8 is the whole way up. So what you can do is say, well, h over 8, okay, sorry, I just want to see if something will work for me here. So your similar triangles are the top triangle, which is h over 4. So, okay. And then the large triangle is h plus 8 over 6. Okay, so in the top triangle, we've got h over 4. In the bottom triangle, we've got h plus, sorry, no, we don't have h plus 8. We just do, yes, we do have h plus 8, sorry, over 6. Does that make sense?
Yep.
And this allows you to find h. So you've got 6h is equal to 4h plus 32. So 2h is equal to 32. Did I do that right? H is equal to 16. So your total height of that cone is 16 plus 8 is equal to 24. Okay, so the large cone is pi. So you've got the large cone is pi by 6 squared by the height of the large one is 8 plus h is 24. And then the small one is pi by its radius is 4 squared and its height is 16. And then you subtract those from each other. So we've got, I'll do the 6 squared, I'll do the numbers first and then by pi. So you've got 6 squared is 36 by 24 minus 16 by 16. And that's 608 times pi. Is 1910. Sorry, it's cone, it's 1/3. 1/3 pi r. So always write down, go to the tables because you do something stupid like that in the exam. Go to the tables, get your shape, it's a cone, look at the volume and write down the formula. Okay, that's classic mistake there. 1/3 pi r squared h. And I want the big one minus the smaller one. So that should be 1/3 times that. So that divided by 3 is 636.7. And I'm rounding it off. So 636.7, correct to 1 decimal place. And that's in centimeters cubed. Okay, now the next two are looking at our tolerances and percentage error and so on. So let me just click over. So Matt weighed 85 kilograms before training and 81 after. Find the maximum and minimum values for his weight loss. So you might just look at that and say 85 minus 81 is 4 kilos. So he lost 4 kilos. But what you want to say is the tolerance, okay, it's obviously measuring in kilos. So that could be anything from 84.5 up to 85.5, okay, because that's his tolerance plus or minus a half. And then it could be anything from 80.5. Yeah, 80.5 up to 81.5. Okay, so that's before and after. So find the minimum values for his weight loss and the maximum. So the minimum would be the smallest before minus the biggest after. Do you see that? Because the minimum would be this minus this. That makes sense?
Yeah.
So 84 minus 81.5 is 3 kilos. And the max would be the other two, 85.5 minus 80.5, which is 5 kilos. Okay? That makes sense?
Yeah.
And if you look at that, if we go back to our original, the tolerance was 0.5, but because we had two measurements, so we would have done the 4, and it's not plus or minus 0.5, it's plus or minus 0.5 by 2. So 4 plus or minus 1 because you have two measurements. So it's, and that gives you the 4 minus 1 would be 3 and the 4 plus 1 would be 5. But the safest way to do it is write down the range for each, and then the minimum is the highest minus the lowest, and the max is the other way around, highest minus lowest from before and after. Okay, so it's common sense really with these, okay? And then the next question would be much more of a typical exam question. So a company makes ball bearings with a diameter of 12 millimeters, and they're produced to an accuracy of 0.02. Find the largest and the smallest produced. Find the percentage area on the, percentage error on the diameter and the volume. Okay, so the diameter is 12 millimeters, and they're produced to an accuracy of 0.02. So that means it could go anything from 11.98 up to 12.02, because that's your error, okay? So it could be plus or minus 0.02 from that, all right? So that means the radius would be half of that, so 11.98 divided by 2. So the radius could be anything from 5.99 up to 6.01. And that's millimeters, okay? So your volume, the minimum would be, and the volume of a sphere is 4/3. So V is 4/3 pi 4 cubed. So the minimum volume is 4/3 by pi by 5.99 cubed. And you can see here your tolerance, your plus or minus is getting cubed here. So it's going to change the tolerance because it's a volume, not just a length. Okay, and if you do that in the calculator, you've got 4/3, and put the pi up with 4. And then you just do brackets 5.99 per 3, and we've got 900.262 millimeters cubed. And then the max, and I can just, with the calculator, I can just go back and swap the 5.99. So I don't have to put it all in again. I just arrow back, delete the 5.99 and put in 6.01. And that's 909.31. So you can see it's quite a difference. It's a 9 millimeter cube difference there. Okay, so the that's your difference in volume. Now the percentage error on the diameter, it goes plus or minus 0.2. So you've got 0.02 over the correct value is 12. And then you change that to a percent, and that works out at plus or, and it's plus or minus, so it's 0.0167%. Now the volume, on the other hand, the correct volume, so V correct is 4/3 pi by 6 cubed. Okay, so I just put that and change that slightly. Is 904.779 if you round it. Okay, so the percentage area and the volume, I can either do this minus this or this minus this. They'll both give me the same. Okay, if I do 904.779 minus 900.262, so the error, the actual error, 4.517. And if I do it the other way around, if I have 909.31 minus 904.779, I get 4.531. So slight difference, okay? So 4.517 over the correct volume, multiplied by 100%. And that gives me 0.5%, and it's plus or minus that, because I could do it, it could be plus that would be this one, or if I did the difference between these two, it's the minus one, and it kind of round to plus or minus 0.5%. Okay, so you can see that the percentage difference in the volume is much bigger than the percentage difference in the diameter. That makes sense?
Yep.
Okay. So that's, I don't think they even give you any questions on that. 90%, okay, there is some. So, yeah, questions 11 and 12. Okay, so you want to go ahead and do those. So we have an easy enough session today. Questions 11 and 12. Okay, and actually, I'll just have a look in the meantime, see if there's an exam question that we could look at as well on that. And then tomorrow we're going to look at the trapezoidal rule, which ties into a lot of the integration questions. So we might go back and look at one or two integrations once we've covered that to kind of pull all that together. So if you want to just try 11 and 12 there, I'll put it up in Classroom and see if there's a nice exam question we can do on that. Okay, guys, just looking back over, the only one I can find with the tolerance or percentage error in it was back in 2011. So they haven't asked this really since Project Maths got off the ground. So most of it is just rounding, making sure that you know how to round. other than that, it doesn't really come up much. So you don't have to worry about it too much. Are they working out okay so far?
Yeah.
Let me just get the old one. Okay, Andre. Andre.
Yeah.
Matthew.
Yeah.
Sean.
Yeah.
Aaron.
Yeah.
Jeff.
Yep.
Thank you. Cordian.
Yep.
Andrew. Ben. Oh,
Yeah.
Jamie. Thanks. Pavel.
Yep.
Alan.
Yeah.
Dylan. Andre V. Andre, you there? Joe.
Yeah. Mate.
Mike. He's not there. And Harry.
Yeah.
Okay, thanks. I didn't mark it.